Example 4 says a cup of coffee has temperature 95 degrees Celsius and takes 30 minutes to cool to 61 degrees Celsius in a room with temperature 20 degrees Celsius. The temperature can be modeled by the function capital T of T is equal to 20 plus 75 times e to the power of negative 0.02 T, where T is measured in minutes. What is the average temperature of the coffee during the first half hour? Round your answer to 1 decimal place. So we're measuring in minutes, and I want to know what's the average temperature during the first half hour. So the average temperature is equal to 1 over 30 minus 0 times the definite integral from 0 to 30 of our temperature function, which is 20 plus 75 e to the power of negative 0.02 t dt. So what I want to do now is I'm going to split this up into two different integrals. I have 1 over 30, and then my first integral, using integral properties, I can do this. And then we have plus 75. I'm factoring that outside of my second integral. And now I have these two integrals that I want to solve. The first one, I can just use the power rule on it. So I'm going to go ahead and distribute my 1 over 30. And then if I use the power rule on 20, that would become 20t. And I want to evaluate this between t equals 0 and t equals 30. And then if I distribute the 1 over 30 into my second integral, I have that. And off to the side here, I'm going to need to use u substitution. So I'm going to set u equal to negative 0.02 t. That's going to give me that du is equal to negative 0.02 times dt. And if I solve this for dt, I get negative 1 over 0.02 times du is equal to dt. So now I'm going to come back here and I'm going to write my integral from u1 to u2 of negative 1 over 0.02 times e to the u du. And let's go ahead and evaluate this stuff. So I have 1 over 30 times 20 times 30. And then if I evaluated that at 0, that would just be 0. And these are going to cancel out. So that's just going to leave me with 20. And then I'm going to factor out my negative sign as well as my fraction. So I have minus 75 over 30 times 0.02. And then the antiderivative of e to the u is just going to be e to the u. And I'm evaluating this from u1 to u2. And now I can switch back to my original limits of integration and put my expression in terms of t. So I have 20 minus this fraction right here ends up simplifying to be 125. So I'll write 20 minus 125 e to the power of negative 0.02 t. And I'm evaluating this from t equals 0 to t equals 30. I was starting to run out of space, so now I can evaluate this. So I have 20 minus 125, and then I have e to the power of negative 0.02 times 30 minus e to the 0 power. That's going to evaluate to be 1. And if you throw this into your calculator and you round to 1 decimal place, you should end up getting that this is equal to 76.4 4 degrees Celsius. So that is the average temperature of our cup of coffee during the first half hour. Example 5 wants us to find the average value of our function f of x equals 1 over x squared on the closed interval from 1 to 3. So now we have negative 1/2 times, if I found a common denominator, that would be 3/3 there. And so I get negative 1/2 times, this would be negative 2/3, and these 2's would divide out, and I end up with positive 1/3 for my answer for part A. Part B wants us to find a value c such that f of c is equal to the average value of our function. So I'm going to go ahead and I'm going to take my function, which is 1 over x squared, and I'm going to set it equal to the average value that we just found, which was 1/3. And if I cross multiply, we end up getting x squared is equal to 3. And then if I take the square root of both sides, I get x is equal to plus or minus the square root of 3. However, we're focused on the closed interval from 1 to 3, so I don't really want the negative value. So we get x is equal to the square root of 3, and that's the value that we are looking for because f of the square root of 3 is equal to the average value of our function, which we found was 1/3 in part A. Part C says sketch the graph of f and a rectangle whose area is the same as the area under the graph of f. So earlier when we were talking about the mean value theorem for integrals, if we are looking at a continuous function, which 1 over x squared only has a discontinuity at x equals 0, and we're not looking at x equals 0, we're looking at the closed interval from 1 to 3, so we are looking at a continuous function on some interval from a to b, then the mean value theorem for integrals says that we can essentially take the definite integral, and that is equal to f of c, which the c value was the square root of 3 from the previous part, and we're multiplying that by b minus a. And so what this is essentially saying is that this is the area under the curve, and f of c is the height of our rectangle, and then b minus a is the width of our rectangle. And what rectangle are we talking about? I'm just going to show you in just a moment what rectangle we are talking about. Okay, so here we have our y-axis and our x-axis, and in blue we have the graph of y equals 1 over x squared graphed. And so if I dropped this down between 1 and 3, and I took this area here, between x equals 1 and x equals 3 underneath my curve, that blue area is the same area as the area of my rectangle, which my rectangle can be seen here. And the width of this rectangle we said was b minus a, which in this case is 3 minus 1, which is equal to 2. And then the height of my rectangle is equal to f of the square root of 3, which is 1/3 in this example. So that's brought to you by the mean value theorem for integrals.